Welcome to your Introduction to Statistics, Unit 6, Lesson 1. Today we're going to talk about using scatterplots or scatter diagrams and calculating correlation between two quantitative variables. We did go into this and coming up with the linear regression model in the finite math portion of this course, first semester, and so we're going to just kind of build on that, and then we're actually going to talk about some ways to actually produce the data that we study through observational studies and experiments. Okay, so if you'll recall, a scatter diagram or scatter plot is just a graph of a bunch of points that are that represent data pairs, x and y values that are related to each other, representing some individual. And so x is the explanatory variable, y is the response variable. So we might be looking at how well a water treatment plant works on removing phosphorus from water. So at different points in time, which would be our individuals, the different samples that we take, we might measure the phosphorus concentration at the inlet into the water treatment facility and the phosphorus concentration at the outlet where the water is flowing out, and we hope to see a reduction. So here we've got a scatter diagram or scatter plot of the phosphorus reduction, and so each point has been plotted, and you can see somebody has come along and modeled it with a linear model. So the red dots, the red points are the actual data, and the blue line is the model. The linear correlation is the general trend of the points. It seems to follow a straight line segment. That's when we determine that we have a linear correlation. And so if you look here, yes, there's scatter, hence the name scatter plot, but overall, as the x values increase, the y values tend to increase at a fairly steady rate. An example of a nonlinear correlation, or which we would just refer to as an association, is right here. There is definitely some sort of pattern going on, but it's certainly not linear. And then where there is no linear or any other correlation at all going on here, we just have what appears to be a random scattering of points. High linear correlation means that we have points that lie close to a straight line. Okay, here's a picture of that. You might want to copy that down. A moderate linear correlation is going to be a little bit more scatter. And low linear correlation, it's going to be hard to see any, a straightforward pattern there. A lot of scatter. Perfect linear correlation, no scatter at all. Everything lines up perfectly. That does not happen in the real world very often. Okay, so if there's a positive linear correlation, that means that if you were going to model it with a line, the line would have a positive slope. So when you have high values of x, you have high values of y. When you have low values of x, you have low values of y. A negative linear correlation means that if you were to model it with a line, the line would have a negative slope. So you're going to have low x values with high y values and high x values with low y values. Little or no linear correlation, it could just be all over the place. Some questions that arise from the data are, can we find a relationship between x and y, and how strong is the relationship? Okay, and is that relationship linear? That's another good question. A numerical measurement that assesses the strength of the linear relationship between two variables x and y is the correlation coefficient r, and it only makes sense in terms of linear relationship. If there's a perfectly quadratic relationship, the correlation coefficient isn't going to give you any information about that. Technically, it is called the Pearson product moment correlation coefficient, but people just call it the correlation coefficient. R is a unitless measurement. There's no units to it. It's not like a certain number of centimeters or inches. It doesn't have any units. Between -1 and 1. So -1 is less than or equal to R is less than or equal to 1. If R is equal to 1, then there is a perfect positive correlation. If R is equal to -1, there is a perfect negative correlation. If R is equal to 0, there is no correlation whatsoever. Positive values of R imply that as x increases, y tends to increase. As we go from left to right, the least squares regression line goes up. The slope of the least squares regression line will be positive. Negative values of R imply that as x increases, y tends to decrease. So as we go from left to right, the least squares regression line goes down. The closer r is to -1 or +1, the better a line describes the relationship between the two variables x and y. The value of r does not change when either variable is converted to different units. So if you have measurements of people's heights and weights in inches and pounds, it's not going to make a difference if the r value won't change if you change the measurement of heights to centimeters and weight to kilograms. That's not going to affect anything. The value of r is the same regardless of which variable is the explanatory variable and which variable is the response variable. In other words, the value of r is the same for the pairs x, y as for the pairs y, x. So that's not going to change it either. So if you want to compute the correlation coefficient, r, you're going to obtain a random sample of n data pairs x, y, and using the data pairs, you're going to compute the sum of the x values, the sum of the y values, the sum of the x squares, sum of the y squares, and sum of the x times y's. Okay, so anytime we have those little sigma, well, actually those are big sigmas. The big sigmas there, that means we're going to use columns to keep track of things. It also means that your calculator probably will do this for you if you learn to use your calculator well. Okay, so we're going to use the following formula, which you will not need to memorize. I'll provide it for you. It's just if you're going to use it, you've got to be able to use it correctly. So r equals n times the sum of the products of x and y minus the product of the sum of x times the product of, times the sum of y, all over the product of two big square roots multiplied together. Inside the first square root, you've got n times the sum of the x squareds minus the sum of x's squared, and that's two different things, times n times underneath the second square root, you've got n times the sum of y squared minus the sum of y quantity squared. So kind of a tricky formula to use. I'm really going to suggest that you learn to use your CAS and find r that way, but we can do this. All right. So let's say we are looking at some data of where people have a certain number of miles that they are going to travel in a certain number of minutes. So we've got some x and y data here of miles and minutes. We're going to leave our phosphorus example. So when there's 2 miles, it takes 6 minutes, 5 miles takes 9 minutes, 12 miles takes 23 minutes, and so on. So we've got our x's and y's. If we're going to do this by hand, we need to know several sums. We need to know the sum of the x's, so we just add all those up. We need to know the sum of the y's, so we add all those up. And we need to know the sum of the x squareds. So we square each individual value. So 2 squareds 4, 5 squareds 25, 12 squareds 144, and so on. Then we add all those up. And then we square each y term. And we add all those up. And we need to know the sum of the x times y. So we take each x and multiply by its corresponding y. So 2 times 6 is 12. 5 times 9 is 45. 12 times 23 is 276. We multiply each pair together, and then we add all that up to get the sum of the products of x and y. And then we plug it in. So we have n times the sum of the x times y's minus the sum of the x's times the sum of the y's, all over 2 square roots. In the first square root, we've got n times the sum of the x values squared, so each individual x value squared and then summed up, minus the sum of the x's, that sum squared, times the square root of n times the sum of y squared, and then minus the sum of the y's squared. This little parenthesis right here should be a minus sign, so don't let that throw you off. That should be a minus sign right there. All right, and so when you calculate all this, you get 0.975. Okay, R can also be found by entering the data in 2 lists in your CAS and running a linear regression on the list like we did first semester in section 1.3. I'm going to be attaching a link to 1.3 along with this video. So if you go back to the email where you link to this video, you'll see that there is a link to the 1.3 video also. If I forget to do that, remind me. That way you can go back through and look at the example on that video and go back through the steps of being able to enter the data and run the linear regression, and then boom, your calculator gives you R. You're going to have to use a calculator anyway to work with these values, you might as well learn how to use your calculator to produce the value for R, all in much fewer steps. Okay, interpretation of R. An R value of 0.975 indicates a strong positive correlation between the variables x and y. It's strong because it's close to 1. If it was negative and close to -1, it would still be strong. It's positive because it's a positive value. And then we say correlation because that indicates the linear relationship. All right, sample compared to population correlation, just so you know, the sample correlation coefficient is R, and that's what we tend to work with. People do use that to estimate the population correlation coefficient, which is this little Greek letter right here that's called rho. Okay, it's a Greek letter. It's kind of cool. The correlation coefficient measures the strength of the relationship between two variables. A strong correlation does not imply a cause and effect relationship. People often make that mistake. A correlation between two variables may be caused by other variables called lurking variables that actually are responsible for both the x and the y value. A lurking variable is neither an explanatory nor a response variable. A lurking variable, like I said, may be responsible for changes in both x and y, and we'll talk about some examples of those in class. Just ask me. I'll be happy to give you plenty of examples. Okay, guys, that's it for Lesson 1. Go ahead and do the problems to trying on your own. Thank you so much for paying good attention, and come to class prepared. I look forward to seeing you soon. I hope you have a great day.